Okay, I think we have everyone. So good afternoon, everyone. I am Nicolo Thoresca, the Inside Technical Sales Supervisor for the Filtration Division of John Brooks Company. This is part 2 of our 3 webinar series on heat exchangers. In this webinar, we'll be covering the industries and applications as well as process variables when selecting a heat exchanger. This will be a bit more technical than the previous session, so hope you're prepared for that one. Bit of an introduction for the rest of the panelists. So the primary presenter in this case is Ross McGowan, the Technical Sales Representative in Filtration Division. Again, he resides in Calgary and has worked throughout Western Canada for about 30 years. And he will also be joined now by June Rivera, who is the Application Specialist for Heat Exchangers. We also have Uday Shastri, who is the Senior Technical Specialist for the APV heat exchangers, which is under the SPX Flow brand. And finally, we have Anita Gupta, who is the Business Manager for the Filtration Division of John Brooks. A little housekeeping again before we begin. Today's presentation will be recorded and the link of the recording will be sent to you afterwards. If you have any questions, there is a Q&A button that feel free to populate questions and we'll answer as best as we can. We want to respect everyone's time commitment, and if there's any questions unanswered after the 1 hour period, we'll address them again in a follow-up email. So thank you very much. And with that, I turn it over to Ross.
Thanks, Nico. Welcome, everybody. Thanks for coming back. As you might have heard, Nico has told you that this is part 2 of a 3-part. We originally decided to have this as 2 parts, and due to the response of our first part, we got too much questions and too many good information from those that were with us. So we wanted to break it down to 2 more additional sessions just to get the information to you. So let's get right into it. We've got a little bit of distance to go today. As Nico had mentioned for housekeeping, there is that question button down at the bottom of your screen. Don't save your questions to the end if you got an idea, if I haven't covered anything for you as we go along. Ask the question then, and we'll probably only get to them at the very end, but ask the question as it comes in your mind, and we'll clarify everything for you as we go along. So without much further ado, what are we doing today? We are going to have a quick recap of what we talked about in the first session, which was the efficient heat exchange and what goes into making that happen for us. And then we're going to do a nice deep dive into plate and frame heat exchangers, gasketed plate and frame heat exchangers specifically. We're going to talk about choosing them, the options, what goes into making a plate and frame heat exchanger fit into your world or your process. And then we're going to work into actually selecting one. So we're going to need to know the technical parameters, your process flow conditions. And then we're going to talk about the green technology. There is a payback from the amount of energy that we're trying to repurpose. Again, we talked about last time how expensive hard-won heat is, whether it's a thermal fluid, whether it's going to be water, direct fired, steam heated, however we're getting heat into our processes, it costs money and takes time. So we want to try and capture that in a green way. And then depending on how much time we have left, I have some industries and some applications at the tail end for us to go through. I've tried to keep them very generic so that they'll suit pretty much everybody that's online, or at least we have a way to adapt them to what's going on in our process. The attendee list today is pretty much border to border in Canada. So from the very far east to the very far west and everybody in between. And we even have some guests from the United States with us today. So thanks very much, everybody, for joining. And let's get into it. So the quick recap again, when we're talking about efficient heat exchange and design, we have to take in our flow parameters and our process data. So we need to know the flow rate and the operating temperatures, obviously too hot, too cold. We need to know the pressure or the temperature differential as well. Of course, we've got to know the pressures, the flows, all that good stuff that's going on there. And then to be most efficient, choosing between a shell and tube or the plate and frame style is we want to know the densities, the specific heats, the viscosities, those kinds of things. Those all will tell us if we're able to use a plate and frame, because remember, a plate and frame is the most efficient heat exchange technology that there is. And that also brings us into the cleanliness and then how much pressure drop we're allowed. So if the more pressure drop you can handle in your system, the more efficient the heat exchange is going to be and the better off you are. So that rough or turbulent pressure drop is all based on the Reynolds number for those of you that are familiar with it. So laminar flow, as we talked about, is really good in piping. It's nice and steady. Everybody stays in their lanes and it flows really easy with the least amount of energy. Turbulent flow, however, in a pipe is not very good. It uses lots of energy, pretty messy, causes erosion, all sorts of things. But in a heat exchanger, it's what offers up the energy into the sides of the pipe, or in our case, to the walls of the plates. And that gives us the energy transfer and more efficient heat transfer. So this is what it looks like in a laminar flow. And as it kind of cycles, you'll see the leading edges through the middle and then the friction on the outside, which causes that very typical sort of chevron shape. And then a turbulent flow, all these waves, all these energy or flow paths are banging into the sides of the heat exchanger and creating an opportunity for the exchange of heat. So we're looking for turbulent flow as much as possible. Turbulent flow gives us differential pressure. So that's really good in a heat exchanger. That gives us efficient heat exchange, captures more money for us. And then we talked at length about plate and frame heat exchangers do not go serpentine through the exchanger. They're header systems. So the inlet of the cold at the top, inlet of the hot at the bottom fills the entire header. And then on each plate pair, it goes up once and then out once. And it's a co-current or cross-current, counter-current flow. So they're going directly opposite each other. And that again is also the most efficient way to heat exchange. And then we talked about at great length when you can use a plate and frame versus a shell and tube. We talked about shell and tubes are essentially welded vessels with piping type gaskets as the only seals. So if your piping system can take what's going on inside of your system, a shell and tube should be able to take it. However, they're the least efficient or mid-efficient in exchanging heat. So therefore they take about 5 to 1. So 5 times the material, 5 times the space, and they have 1/5 of the efficiency, give or take. It's kind of a rule of thumb. And when you start talking about plates and gasketed plate and frame heat exchangers, they are limited for their temperatures and pressures, but they're tremendously efficient relative to a shell and tube. So let's dive in and talk about some gasketed heat exchangers. First thing you want to be worried about or talk about is, can I use them in my system? People are worried, that you have to use ASME. Obviously in Canada, we need CRN, and fear not, all APV heat exchange and all plate and frame heat exchangers by other manufacturers, as far as I know, they're all CRN all across Canada, ASME made. So all those codes and standards are up to speed, and they're used everywhere in the world. There's not a country or an area that is not using plate and frame heat exchangers. So should you have to send projects into the Middle East or into Africa or Asia, by all means, you're going to be able to meet the codes and standards of the local area and classifications. So take all that worry out of your mind. It's more about the process, not the codes and the standards. So we'll be able to get that. So let's talk about the components of a heat exchanger. There's several things that go into making a plate and frame heat exchanger. Obviously, plate and frame has got plates and frames. So here what we have is we have a support bar and a carrying bar and a bottom bar. So those are going to carry the weight of the plates and they're going to keep them aligned. And then we have a first big plate that you've all seen. This is the one that goes forward to dimensionally close the heat exchanger, and it's called the follower, so because it falls along the top bar. Then we have the header, and this is where our end connections are going to be. So whether they're going to be flanged or nozzled or gas or threaded, that's what you've got. And then of course we've got some plates, some gaskets, and then a few more plates, and a few more gaskets, and a few more plates, and a few more gaskets. So we make up a plate pack, and then we add tie bars. Now you can have as many as 12 tie bars in these things, because you can imagine if you have a 12, 14 foot tall, 12 inch, 14 inch, 16 inch inlet end connection heat exchanger, and these things could be 4 feet wide. You need a lot of force to close these things. So the tie bars go in, and we dimensionally close the heat exchanger so that these things are not closed by torque values or anything like that. They're closed by dimension. So it's the inside of the header to the inside of the follower. That's how they're closed. And it's all made up by dimensions of the thickness of the plates themselves added to the thickness of the gaskets. And then you just multiply by the number, and it's a dimension, and it should be something very, very close, you know, 1.5 centimeters, 2 centimeters between closing them and not. So very standard. That's all the parts. And we'll just blow it up again just so you can see it, and we can talk about the headers and how they all work, and the gaskets. So the real magic between what a plate and frame heat exchanger is of course the plates and the corrugations and the gaskets. So all of those things have to work in concert to make sure that this thing gives you such efficient heat exchange and long life, long runtime. They work fantastic. So again, the header, it's not serpentine. It doesn't go every second plate pair and wind itself through the heat exchanger, then come out. It fills the header, and then it comes down each plate pair all at the same time, then fills the outlet header, and away it goes back out. And the exact opposite for the cold. And you can see how they're countercurrent. So one's going all the way up, one's going all the way down, and they fill their headers entirely, go through the system, and then fill the outlet headers. And again, we have a carrying bar, support bar, the header, follower, bottom bar, and then tie bars. So all these guys work together, and that's all the components for it. There's no moving parts. Once we get this thing closed, there's nothing to worry about, you know, no impellers to fix, no brushes and motors. These things get closed and they work for years and years and years. Pretty simple. The magic of a heat exchanger, and a plate and frame heat exchanger specifically, is the corrugations on the plates, and they're designed to give the most heat exchange units. And these corrugations can be done at different angles, and we'll talk about that in a minute. But they're all designed to remove the heat specific to your application, specific to your flows, specific to your fluids. So we can change these things to maximize the heat exchange given the differential pressure that you're allowed to have, or the viscosity, or whatever other process variables that we have to take into account. Now, how these things work, and remember how we talked about their headers. So the gaskets themselves are sort of 3 different parts. They have a header gasket and a flow gasket. And then you can see that there's some little channels here. And we'll talk about those in a sec, but the header gasket itself is what keeps the fluid going in between each specific plate pair. So it'll be left plate, right plate. So in this case, we have a right plate because there's no header gasket, and it allows the cold fluid in this case to come in, go through the distribution channels at the top, or in the bottom in this case because it's cold. It will fill up the entire width of the plate. It will go over these corrugations, creating that turbulent flow, getting us a nice high Reynolds number, exchanging, or in this case, collecting the heat because it's cold, it's gonna be warmed up, and then it hits the collection channels on the opposite side, and then back to the header, and then back out to wherever it's supposed to be used. So we have the flow gasket here in its plates channel. There's a little groove that I'll show you in a sec. And then we have the header gasket, and this whole flow gasket is what keeps it in its individual plate pairs. So if we zoom in on the header gaskets, there's sort of 3 ways here that we have protection from cross-contamination. We want to go to each individual plate pair and make sure it does its work and doesn't intermix. We don't lose any efficiency, and we don't lose any fluids. So the first line of defense is, of course, the header gasket itself. Sits in its groove, gets compressed against the plate in front of it, stays in its groove, and does its work, and keeps the fluid moving to its proper plate pair. It skips every second plate, so hot goes to hot only, cold will go into cold only. Should there ever be a failure in this gasket for whatever reason, there's vents. So those little tiny holes that I showed you in the previous slide, they're actually there on purpose. So they're little vents that are allowing the hot fluid in this case to vent to atmosphere so it doesn't intermix through the flow gasket. So we've got 3 areas of protection. So we've got the header gasket itself, we've got the vents, and then should something go wrong with those 2, we still have the flow gasket keeping it safe. So should you ever have a failure or a problem with the gasket and you see weepage or leakage, that is a sure sign that you need to do some maintenance. And that's what these things are there for. They're there on purpose to let you know that you have something going on, and it's now time to look at it and prevent intermixing. And then, of course, we have the flow gasket around the whole way. And these things vary. So, they alternate, sorry, not vary. We'll have a right plate, then a left plate. And we'll just see right now how they look, or sorry, in a couple slides. But we'll talk about the gaskets and the grooves. So there is 2 ways that we attach the gaskets. The old school way, and still in alive today, but not as common, is gluing in. Works great. You can imagine you put some glue in the groove all along the plate, drop the gasket in, press, hold it, let it cure. Sometimes you have to put it in an oven, depending on the style of glue. And then you have like a nice cured gasket onto a plate. Should you ever need to maintain those things, you got to do the exact opposite. You got to soften the glue, you got to clean the groove, and then you got to reattach gaskets. Over time, pretty much every manufacturer has come up with a system to press in or clip in gaskets. So instead of gluing and curing, they now have little sprues on their gaskets, and they'll have some alignment tool, whether it's going to be in the edge of the gasket or edge of the gasket groove, or some kind of hole in the gasket groove, this whole groove is non-wetted, so everything's inside here in the flow path. They'll put those little sprues, it'll match up and align with where it's supposed to in the gasket groove, and away we go. So you press the gaskets in the whole way around. Labor savings is tremendous, and then of course it's easy to maintain, and they stay in the groove just fine. So pretty much everybody has gone to those as a manufacturer. Still can do glue-ins if you have old sort of legacy type machines. Chances are excellent that you're going to be looking at press-in or clip-in gaskets moving forward, if not already. So we have a statistic that says 80% of the units and machines out there are already pressing gaskets. So very common out there, working all over the world in all sorts of applications, and very successful. And how that works is if we do a cross section, so this is the face on of the plates, and now we have a bunch of plates stacked. So we're making a plate pack here, and we have the cold fluid through here, hot fluid through here, cold fluid. So this is the flow side of the plates, and then this is the outside to atmosphere way out here. And that's the gasket groove that I talked to you about, that we either push those spools into, or in the old days, you would have glued along the bottom of each plate, put the gasket in. In this case, we're going to press them in or clip them in. And then once you make the plate pack, you stack them or hang them off the carrying bar. They're going to mate up with each other. And then when we dimensionally close, they're going to compress the gaskets, completely filling up the groove and thereby sealing. So super easy to do. The plates are manufactured and pressed in a way that they will align so that they'll all fit together and everything does its proper good. So we talked about the header gaskets a couple seconds ago. So you can see here we got a header gasket and then an open. So we have the cold side going here, and now we have a left side plate. So we got rid of the header gasket, so now the hot can enter this plate pair. And then the next set, it flows through the hot plate, goes back into the cold plate. So every second pair has the appropriate fluid. So it'll go cold, hot, cold, hot, cold, hot, cold, hot. Flow gasket keeps it inside, header gasket keeps it in the header. And we do that for as many plates as your plate pack is intended. All these grooves or corrugations are designed to release the heat and give you the most turbulence and pressure drop as you need for your system, minimize the plates, maximize the efficiency of your heat exchanger. So let's talk about those chevrons or the corrugations. They're designed based on the plates, based on the fluids, based on the thickness of the plates, and they can have a variety. They can be as much as 60 degrees, 50 degrees, 40 degrees, 30 degrees, and then on down to 0. And really they're designed to be custom put into your heat exchanger so that we can maximize the differential pressure, the Reynolds number, and get all that nice turbulence so we can extract as much heat as possible. So if we look at this plate, which is a 0 degree, which is going to be a long thermally long plate, meaning it's going to take a long time or longer time for it to go over this corrugation versus this corrugation. Less turbulence here, more turbulence here. So you're going to extract more heat, but you're also going to get more differential pressure. So if we can only have a specific differential pressure, we're going to have to mix some of these. You can have a plate pack with different 50s and different 0s or 60s and 30s. It's all based on differential pressure in the fluids. They all essentially operate the same in the distribution channel, meaning it's going to come through its header, it's going to hit these little channels, and it's going to distribute it. So you get it all the way across, and then it's going to hit and move all the way, fill up the entire side, edge to edge of the plate, go over the corrugations, and then get recollected and back out the header. And it's going to be squished together with a whole plate pack. So as we tailor the plate pack, you can see that thermally long or thermally short is going to have a dramatic impact. So if we have an entire plate pack made of 50s, you can see that it's going to just come through there a lot quicker than if we have 50s and zeros. So this is going to be a much rougher thermally long flow path. So we're going to get more heat, more differential pressure. Here we're going to get less heat, but less differential pressure. So it's a tailor-made plate pack based on your exact process. And this is true for anything. And you can change this over time. Should your process change and you want to extract more heat, you can afford more differential pressure, new plate pack, different plate pack. We can slide things in. That's kind of the beauty of plate and frames, is as things change, it's just a plate pack. So whatever you're doing out there, we can grow with it. We can change with it. It's not a commitment other than when you get the plate pack, it will only do what it's supposed to do based on its corrugations and its differential pressure. So we're going to talk about a couple of more options that you can decide with your plates and with extraneous or extra add-on equipment. So very typical, everybody understands that you can get a single plate. It's got a gasket on it. We just talked about all those, how they work. We talked about sort of the 3 phases of protection to keep it in its header. Should you need additional protection to make sure, absolutely make sure that there is no way that the plates can contaminate. So the headers are going to be fine, but now what happens if there's a pinhole in the plate? What happens if something goes wrong with the plate? We can't have intermixing of the fluids. So there's a duo safety plate. Essentially, behind each plate, there is an added non-gasketed plate. And this air gap in between them means that should something escape from the plate in front of it, it will hit this non-gasketed plate behind it and then leak to atmosphere. So there's no way that it's going to get through this plate and then this plate because it's not gasketed. So it will just leak. And it's intended to do that. So for instance, if you have domestic hot water, you can't get glycol from the boiler into the, your hot water for the condos or for the public to consume. So very common that they're going to use a duo safety, and there is absolutely no way that the fluids can intermix. They will intentionally leak to the bottom, and that's all by design. So once you see anything that's coming out, you know that you have to do maintenance. And then we talked last time about welded plate pairs, and what these are is every plate comes in a welded plate pair. So here we have welds around the entire outside surface of the plates, and those plate pairs are now put together by gaskets. So what this is for is if you have something that you absolutely cannot have get to atmosphere, you can't have any leaks to the ground, can't do anything like take even a remote risk, you're going to have that entirely contained in here by welded plates. So should you have hydrocarbons you can't let out, ammonias you can't let out, anything like that, it's fully contained within a welded plate pair. And then you have the ability to actually maintain the outside by the gasketed plates. So you can take each plate pair apart, you can clean both sides on the outside, and then put it back together. So it's well maintained. This is actually quite commonly used in things like amine, ammonia, and some hydrocarbons. So those kinds of applications are common out there. So we're going to continue talking about the options you can get for plate pairs and inside your heat exchangers. In the decision tree, if you can use a plate and frame heat exchanger, we talked about pressures and temperatures, we talked about fluids, but really what plate and frames love is they love liquid to liquid service, water to glycol, diluted bitumen to glycol, water to water. Steam in some cases is absolutely fine depending on, as long as there's not too much steam by percentage. Liquid to steam is very common. No problems. And then once we start getting into things that we have to start looking at is liquid to gas. Plate and frame heat exchangers don't like gas very much. So it is possible, but we have to look at that as a specific case-by-case basis. And then to multiply that risk up, gas to gas is really unsuited for plate and frame heat exchangers. So liquid to liquid, really good. You got some steam, some kind of vapors in a limited degree for sure. And then as we get into more gases and then gas to gas, plate and frame heat exchangers are not very well suited to that. So liquid to liquid is really where they like to live. And then we talked about the pressures and temperatures on that big chart that we had. Essentially, it's below 400 degrees Fahrenheit is kind of the way I remember it. It's really sort of 375 degrees Fahrenheit, but a 400 degree sort of rule of thumb is if it's at or above that, we're moving on or out of gasket elastomer gaskets territory. Becomes tough to seal. And then operating pressures, sort of anything again at 400 PSI. So if we're below 400 and 400, we have liquid to liquid, maybe some steam, we're good to go. So plate and frames are alive. And the next thing we have to consider is there's a lot of torturous paths in this plate pack. So we got to make sure that they can handle it and be successful. So a lot of applications are going to have some kind of suspended particles, some total suspended solids or TSS. Because of the torturous path and the plate gap, we need to make sure that we understand what is going on in there. So if you have small particles that are nice and round and uniform, typically anything that's a 1/16 of an inch or smaller will fit through these gaps no matter what. Be super easy, keep the plate and frame heat exchanger running without fouling and making buildups inside of there because of that. Should we start getting a little bit bigger, essentially double that, we get to 1/8 of an inch diameter. We can now tailor the plate pack not only with corrugations, but we can make a wider gap. So the gap between each plate is actually a little thicker, a little wider to allow these kinds of particles to fit through just fine. And again, we get nice long run time, preventing fouling, and the heat exchanger will run just fine with it. Once we start getting above 1/8 of an inch, we have to start thinking about pre-filtering. We here at John Brooks are experts at filtering in all ways, shapes, and forms. So just because you have things that are larger or long and stringy, that shouldn't stop you from considering a plate and frame heat exchanger. We can definitely help you about the filtering, pre-filtering, no matter if that's going to be raw river water, well water, pulp and paper with stringy pulp in it. We can get you there so that your plate and frame can have nice long run time. And then, of course, materials of construction. Are you allowed to have carbon steel? Typically, the header and follower are going to be epoxy-coated carbon steel. You can get them made out of other materials, but standards are carbon steel. And then the plates themselves, they can be made typically out of 304 and 316 stainless steel, but all sorts of other alloys as long as they're pressable. So that just means that they're going to be soft enough or malleable enough to take pressing and not crack and be too brittle. And there are all sorts of, SMOs and titaniums and duplexes, all sorts of that kind of stuff is very common, or the common sort of special plate forms. So here's just a little bit more explicit look at the temperatures that gaskets can hold. So very common gasket materials for all plate and frame manufacturers. Of course, they have the rubbers, Vitons and nitrils and neoprenes, EPDM, and then special gaskets. Paramine is an interesting one, certainly for the Alberta folks, but anywhere that there's amine. So if you have amine service, paramine is the gasket we found the most success for. And we're usually using that with a welded plate pair. So we keep the amine between the welded plates, and we use paramine gaskets for the generally whichever side that they prefer. So you can see that, I mentioned 400 degrees as a rule of thumb, just because I can remember it, but it's 375 is really kind of the top end of temperature that most elastomeric gaskets can take, certainly for heat exchangers. So there are lots of options. Once we've got a plate and frame heat exchanger, we can handle the fluids, we can handle the pressures, we can handle the temperatures, we like the materials, everything works great. There's some things to think about now before we get into designing a system or putting it in. And these are all sorts of add-on options that are a lot of times looked at after the fact and go, oh, if I had just known, or if we had have just done this before, the thing would have, our system would have run great. We would have decreased maintenance. We would have increased runtime, increased efficiency of the heat exchanger. And we're going to talk about the efficiency and costing of heat exchangers, what we can recoup in a few minutes. And all of these options are going to help us recoup much more money and much more runtime over time. So things like shrouds, which are, if you can see these guys here, they're aluminum shrouds, which cover the plate pack itself and keep it dust-free or contaminant-free. Or should you have something inside of that heat exchanger that absolutely cannot get on personnel, a shroud is a great choice because it just keeps everything inside the heat exchanger dust-free, clear, or keeps the fluids for sure in. And then of course, they'll add a drip pan in a case like that. So you can contain all the fluids that are inside the heat exchanger from getting in the ground or contaminating anything. So you have a shroud and a drip pan, very common. There are lots of filter options. An inline filter is also one of the common things that APV has been doing forever. I'm sure the other manufacturers have been doing forever. And essentially you get a basket strainer inside the heat exchanger yourself. Now, this looks like an end connection that is on the header. This picture is actually the follower. So that's the big back plate. You have to put an end connection port on the back so you can get the strainer in and out. Obviously, if this was on the end connection on the header, how do we get the piping off to get the basket in and out? So it comes out the backside, but that's something that has to be decided way before you order the heat exchanger. So if that's not something that you're interested in doing, you can do outside pre-filtering. We can do inlet filtering, strainers, you name it. So all sorts of options, grounding lugs. Tie bar protection is also something that's very common. So we put wraps, essentially PVC covers on tie bars so that when they get bashed into with forklifts or anything over time, certainly dust and grease in the environment, keep the tie bars greased and protected so that they can actually do their job when it is time to do maintenance on your heat exchangers. So I did talk a little bit about pre-filtering. That inline filter that we showed the picture of is a fantastic option. Should there be need to do it in outside of the heat exchanger, we here at John Brooks are experts at it. We can do manual or automatic filtration, whether it's going to be a strainer, a bag, a cartridge in a vessel before the heat exchanger. We can do strainers. This particular one is a duplex. We can do any sort of setup that you need. And then of course we have automatic filtration, everything from cyclonic inlet separation to mechanically cleanable and backwashable. So we would be able to tailor you based on your fluids, based on your particle size, based on your total suspended solids, your dirt load. We would be able to work with you to help keep the run time and the fouling as minimal as possible, and the fouling and as maximum as possible on the run time. So this is all things that we do very well, very commonly. If you're using other brands of heat exchangers or just have filtration interests in general, offline, we can talk to you about that at great length. It's what we do every day. So now we're going to talk about, we've decided that we can use pressures and temperatures, our fluids, we have filtration looked after, we can use a plate and frame heat exchanger. Now we're going to go ahead and we're going to call Ross, or we're going to call June, and we're going to get a plate and frame heat exchanger used. So we're going to need to know some stuff from you. Obviously, we'll know who we're talking to and what you're doing. We generally, and I personally prefer to have a project name, not just, you know, this is Ross's heat exchanger. If you're working on a project or you have a tag number, we definitely like to know that for you so we can keep it straight. And then we need to know some stuff. We need to know what fluid you're using. We need to know, you know, if you can't tell us the names of them, we need to know, are they condensable? Are they specific gravity? Any of that kind of thermal conductivity. We have a tremendous sort of library of fluids that we can help you with. June, when you're working on these kinds of things, when they're talking to you about sizing a heat exchanger or got a process for you, what kinds of things do you want to know or do you like to know to make everything work best?
Like you mentioned earlier at the very start of this presentation, we need the operating conditions, right? So we need the flow rates, the operating temperatures, pressure drops. If you have the fluid characteristics like that, the density, specific heat, thermal conductivity, and viscosity, well and good. But if you don't have, like you said, just like we have a very extensive database that has all the properties from chemicals, acids, bases, cosmetics, even food, oil and gas, lube oil, service fluids, alcohols, we have those in our database. So unless it's a very specific kind of fluid, like say in the lean-rich amine, they usually have all the properties I specified when they're sending their inquiries. So yeah, so basically that's all I need.
So when you're sizing or when you're working with the customers on selecting their heat exchangers, this is essentially the work screen that I've seen, and I'm sure it's the same one that you're using pretty much every day.
That's basically the data entry screen, and you can specify the hot and cold mediums, and of course all the flow rates and temperatures in the pressure drops. So
How many of these variables do they need? Do they
we need at least 5, excluding the pressure drops, of course, just to balance the equation.
So you'll need like inlet temperature of the hot, for instance, or if you need inlet temperature for the hot, so you have
in this case, all for example, just like the flow rate, all the ones that are not highlighted, those are the ones that were given in this specific RFQ. So you can see the green ones; those are the ones that were calculated values. So.
Now, this is a real world selection that we've had from a customer actually fairly recently. And it's just 1800 gallon per minute water, warm water too. It's only 100 degrees hot coming in. And then you're using some kind of cooling water, which is 85 degrees coming in. And they're heating that 85-degree water up by 10 degrees. And they were allowed to take 10 PSI pressure drop on both sides. What blows me away about this thing is it seems like a fairly simple application and not much heat in, 10 degrees doesn't seem like much to me, but we're getting essentially 9 million BTUs per hour out of it. It's a tremendous amount of energy in such a sort of run-of-the-mill application. I mean, 1,800 gallons is a lot of flow, but 9 million BTUs an hour, that's the green part of heat exchangers that it continues to amaze me. And I think we're going to talk to Uday here in a second. He's going to start talking about 9 million BTUs an hour, what kind of payback that we can suck and repurpose out of just warm water, 100 degrees. That's essentially not even as hot as most people like their hot tubs or their baths at home. So it's a lot of energy.
Hey, Ross, we have a question as it pertains to the different type of fluids.
Okay.
Are there any special requirements for plate heat exchangers for highly corrosive fluids? We're talking about something like 10 weight % hydrochloric acid.
June, you've had experience with that kinds of fluids. Generally, the metallurgy of the plates and the gaskets is just fine, but have you ever used one with that specific percentage, June? Oh, you might be muted. Typically, yeah, sorry, did you catch the question there? They're talking about hydrochloric acid, 10%, I believe.
Yeah, I think so. I can look into that further, but I can probably just like give you an answer just like offline, or
yeah, we'll keep going.
Yeah, we do have just like for highly corrosive it's like fluids, we can use just like just like a titanium hastelloys, just like C2000, C276 and all that. So
yeah, so my experience is generally with corrosive fluids, it's an elastomeric gasket question, not a metallurgy. So we can, if it, stainless steel and titaniums and hastelloys and all those sorts of pressable metals are common options as plate packs. If the gaskets that are sealing everything can handle it, it should be no issue.
Can I just chip in with something here? In plate heat exchanger, when we select a plate, it has to be corrosion resistance. There is no allowance like in shell and tube. You can keep on adding the allowance on the plate, right? On the tubes, like corrosion allowance. That's not the case in plate heat exchangers. If they are thin plates, it has to be corrosion resistance material. Anything which is pressable can be used as a plate material. Off the top of my head, if it is a hydrochloric acid, we may not have a right plate material at certain percentage, because probably graphite is the one which is which cannot be pressed by the plate heat exchanger. But we can look into the other different material that we have, like hastelloys, and as June said, hastelloy, titanium, and so on. But the most important thing is it should be completely resistant to the corrosion. That is the material we use. Otherwise, we just will not be able to offer.
Yeah. So thanks, Uday. That was Uday Shastri. So yeah, again, it's essentially a metallurgy issue, so if the gaskets can handle it, if we can contain it with a pressable metal plate, no problem. And I think I can hear June typing in the background, so he's checking into it for us as we go. So this is essentially what happens. You give us your process data sheet. We can add the variables in there and make sure we get a solution for you. And then according to our software, we're going to actually go into the massive library of heat exchangers and get you plates that's going to decide the corrugations, meaning if it's going to be thermally long or thermally short. And of course, the gaskets that are used, because the fluids that are plugged in here determine all sorts of things down the chain for us. So once we'd handled this particular input, it gave us a solution. So this is the actual data sheet that came from this selection. This is what June would have seen when he put all the parameters in and decided to give him a solution for it. So we can see the flow, or the fluid, sorry, are water by water. It gave us the mass flow in conjunction with the actual gallons per minute, or the flow rate. And then the temperature. So all these things are what you would have provided us as a customer. And then the rest of this is essentially what we'll be able to tell you. So if you can handle 10 PSI pressure drop, which just under 10 is what this calculation gave us, that's the 9 million BTUs per hour, which is a tremendous amount. And then this is all sort of from the process data here. But here's your machine down here. This is everything that it solved for us. So we've got frame. This particular frame was an M10, which was able to handle 129 plates. The plates are down here, which are 0.4 millimeters thick, made out of 316 stainless steel. And then paraclip is those clip-in gaskets we talked about a few minutes back. We have the dimensions, which are 85 inches tall, 35 wide, 55 deep. So 107 plates are going to make 55 inches with their gaskets. This heat exchange area is going to be just over 1,100 square feet. It's going to be ASME Section 8. It's going to have a use stamp. It's going to be CRN registered, and then some sort of shipping dimensions and weights and things like that down here. So when it's full of fluids, it's going to be essentially 6,000 pounds, and empty, it's going to be 53,000 pounds. So pretty big machine, but it does a tremendous amount of heat exchange, 9 million BTUs. Along with this will come a sketch, which will give you some preliminary dimensions of end to end, top to top, side to side, plate pack, that kind of stuff. But that's what we need to know. We need to know your parameters, and we can give you a great list of information from there. So once we have all this stuff in, just to make sure if a heat exchanger actually can save you the kind of money that we're talking about, Udo, do you want to talk to them a little bit about payback and costing? I know you've done great work with that over the quite a while. So why don't you take a few minutes and talk to us about the payback on a heat exchanger, if you would?
Yeah, sure. As Ross said earlier, PHEs are very efficient, and they provide most economical solution for most of the liquid to liquid. But especially in heat recovery, they have a unique applications, and basic characters of heat recovery applications or beauties really fit well with the plate heat exchangers. Say, for example, to start with the crossover temperatures, right? So if you see this graph, the hot side in is, the hot side in is here, hot side out is at the end, cold side in is at the beginning of that blue line from the bottom, and then the cold side out. So crossover temperature means that the outlet temperature of the hot side is lower than the cold side outlet temperature. So that's the type of thing which we need when there is a heat recovery application. Just in the previous example that June and Ross was talking about, there was 100 was the inlet temperature and 90 was the outlet temperature on the hot side. And on the cold side, 95 was the outlet temperature, which means that you can cool it further, like the hot side outlet is lower than the cold side outlet temperature. The second one is, I'll just go back, please. The second one is how close these two red and blue lines are. The closer they get, it's good for the heat recovery, but it is the tough application. That can be done in plate heat exchanger. The third one is high NTU, which means that how long is the thermal duty requirement? Whether you're cooling from 190 to 100, or you are just cooling from 190 to 120. So all this can be done in a plate heat exchanger which has a true countercurrent flow. I think more like the next slide will give you some calculation and give you, instead of talking theory, this would probably help in understanding. This is an application where hot liquid, at the bottom of the slide, you'll see a hot liquid, 60,000 pounds per hour of water at 200 degree F, and the cold side is 60,000 pounds per hour of water at 100. We tabulated this with different heat recovery percentage. If you see, that is all the way from 60% heat recovery to 60%, 75, 85, 90, and 95% heat recovery with two pressure drops. One is 12 psi pressure drop, and another is 25 psi pressure drops, because these pressure drops are sort of a price paid for the heat exchangers. We prefer slightly higher pressure drop, but not necessarily like, we need to have a comparison to see what's the cost for a heat exchanger for a given pressure drop allowed. So if you see, the first one has a 40 LMTD with 60%. Actual MTD is 39.4 because it's a multi-pass unit, and you need to have there is some sort of a co-currency in between plates. So area required was 85, and as you see, the price is 5,500 on 12 psi, and at 25 psi, slightly less, but not that much. So if you go through all this, you see, and then the last one is the 95% regeneration, where you are able to heat the cold side of water from 100 to 195 degree Fahrenheit. The cost of the heat exchanger is 18,100. But if you try and calculate payback period for this 95% heat recovery, assuming $10 per 1,000 pound of saturated steam, that number may be different. I'm just saying this for the calculation purpose. You will recover this 18,100 divided by 57 in 317 hours of running this exchanger. So you will see that 317 hours is not much. If it is like 10 hours per day, it's in 31 days you will recover the heat. And after that, you have a free heat exchanger in a way. Many of these things for the plant personnel still need to be educated on this heat recovery. Is possible with plate heat exchanger, because most of them are very conversant with shell and tube, but not exactly plate heat exchangers, and giving them these options may help them to understand more about plate heat exchangers and the advantages. And you can also see that this next slide is the same one that I think Ross did earlier, with 9 million, almost 8.9 million BTU per hour. This is a real cost. The heat exchanger price for this is $35,000. It's very close to real pricing, I believe. So payback period is just 392 hours for this. Again, assuming the same $10 per 1,000 pound of steam. So if you see any of the process fluid or process water or any hot water in the plant, you can recover heat. 90% of the time you can recover the heat using a plate heat exchanger, and the payback period is very low, as you see. So,
awesome.
So Ross?
No, thanks. I find that just incredible. All these years I've been doing this, and just that kind of payback and that kind of energy in a heat exchanger just impresses me. There are no moving parts. We're just conserving, repurposing already used, already hard-won, expensive heat. So thanks for that. That helps understand it a bit now. We're sort of running short on time. So I'm going to blast through some of these slides and where do all these heat exchangers live and where do we have them used? Well, pretty much every industry has utilities, every industry has process. So nice long list here of, you know, pretty much every industry in Canada, every industry in the United States, Europe, you name it, wherever we're at, there are industries where heat exchangers and plate and frame heat exchangers are used. I can't go through these in any great detail today due to time, because I want to get to some questions, but you can see there's just, you know, this is just a quick list off the top of our heads that we can get to and where they're all used. Lots and lots of them. I had some line drawings put together for us that can be tailored to specific industries, but you know, we have incoming water where we filter it, we pump it, we can filter it, heat exchange, then return it back to its pond or back to its river, and off to the plant it goes to, you know, jacket cool or whatever we're doing. These are really common, whether it's going to be a cooling tower or free cooling. Well, we're using lake water, district cooling in this case, but it could be using for heat, just the exact opposite. So all sorts of places that we can use these things. Nico, do we have any questions? I think we're getting close to the hour that we, you know, I don't want to go over. I want to spend time on any questions that we can help people understand.
Oh yeah, we have a few questions, and because we're actually covering applications, this is relevant. So we have a question. Can you further elaborate on applications in which cross-contamination is critical not to occur, and do shell and tube offer any safety or only plate design?
I'm not sure of the safety designs on shell and tubes. Again, I apologize. I'm not an expert on them. I'm a plate and frame guy. We can certainly look into that. I do know that they have corrosion allowances and those types of things when they're designing their tubes and their shells. So that might handle that in their corrosion allowances. In terms of cross-contamination, that duo safety plate design that I showed you is alive and well in many, many places. I generally talk about it in domestic hot water because it's generally the most easily understood. You don't want obviously glycol getting into your bath water or trying to wash your hands with glycol on them when you're in your condo or your office building or your plant for that matter, where everybody's working every day. But it certainly can go into other, you know, non-compatible fluids. Should you want to, you know, have lean-rich amine, for instance, or even just glycol can't get into whatever else you're trying to capture heat from.
To add to that, Ross, it's also just like for mostly for the food and beverage applications. So.
Absolutely, yeah.
Yeah.
Yeah, which you don't want ketchup getting into glycol.
And then we have a question as they pertain to maintenance, actually. So does John Brooks offer a CIP system that is able to service the heat exchangers?
Those are a design by design basis. The pump is the magic in a CIP system. Those are used in industrial heat exchangers for sure. Very common in food and beverage. Can be done, has been done. So absolutely, probably should talk to you offline and get some more details and definitely get that looked after for you. That is for sure something that needs to be thought about before the installation or before the system has been built. Piping changes after the fact are very difficult.
Thank you. Okay, and if my existing plate heat exchanger has a gasketed pack, can I actually replace it with a welded pack?
Yes. So when I looked at that data sheet with you, I talked about the frame, which was able to handle 129 plates. And there was 107 plates in that plate pack that we put in there. One of the great things about plate and frame heat exchangers is they are tailorable. So once you have the frame, you can put a plate pack in there, whether it's going to be gasketed, whether it's going to be plate pairs, all welded is not something that you would typically do in a plate and frame. You would go to a different design for that, but welded plate pairs for sure. Once you have the frame, if you have drop-in plates, they're all the same dimension and they'll fit in the frame and you can switch in and out as needed.
All right, thank you. And I know we had looked over the application data sheet, but do we have a list of standard questions that I can ask from a manufacturer of a plate heat exchanger to evaluate the fit for my particular application? And leading on to that, so why should I pick one plate heat exchanger over the other?
So if we're talking about shell and tube versus plate and frame, I think we've hopefully covered that off very well. Heat exchangers are essentially, they all do the same basic thing. So you have a plate, you have a gasket, you have a plate, you have a gasket. The magic in a plate and frame heat exchanger is trying to maximize the heat exchange, increase that Reynolds number with the least amount of metal possible. So the best design is going to give you the differential pressure and capture the most heat with the fewest plates in the smallest design possible. So that's really the defining line that, you know, you can see one quote for $12,000 and another quote for $15,000. And it's just because, you know, the plate pack in that design sense is a little more efficient in that specific application. And then in terms of a list of questions, I do have a generic spec that I've helped customers with in the past that gives them sort of a cover for what they can look for when they're going out for their bid packages. And I can certainly help them with that. Been working with engineers in design and for decades, so there shouldn't be too much I haven't seen and been able to help with.
Okay. Yeah, we do have a few more questions, but you know, in the interest of time, and actually with respect to the page we're on now, if we can get into that, we'll answer the questions. It doesn't seem like we have additional questions, but we will answer them after the fact.
Okay, I apologize for those that have asked. We're up against the hour. Just really quickly before we let you go, part 3 is going to be talking about heat exchangers in your facility. So how critical are they in your process systems? Generally, they are incredibly critical. They are absolutely, you can't run your plant without them. We've seen how much money they can save us and the green technology that they're offering. So we're going to talk a little bit about what metrics are you using to track them in terms of performance. How do we know that they're doing what they're supposed to do still? Over time, they're going to degrade. Heat exchange is going to degrade due to fouling or, you know, just the general buildup inside of them. So we want to know what we're doing to track them. We want to know what you're doing for a maintenance schedule. We'll talk about those. We'll talk about plans with redundant and duplicate systems and duplicate parts and ready to go to make sure your critical heat exchangers keep on site for you and running, increase your runtime. So with that, we've already talked about questions. There's your 3 presenters. Very happy to have helped you today. And I apologize for not getting to all your questions live, but we will certainly address them after, and appreciate you spending an hour with us today. Thank you very much.
All right, thank you very much, Ross, June, and Uday. As always, we'll have this session recorded, and this will be sent to you after the fact. There's a lot of technical details here to unpack, so for sure, if you want to review it, it's going to be there. And again, we hope to see you again in the 3rd session.